I welcome you all for this lecture series on deep learning. In this lecture, we'll briefly discuss about what is sparse interactions in convolution neural networks. We'll see one by one. First, the definition of sparse interactions. In traditional fully connected neural networks, every neuron in one layer is connected to every neuron in the previous layer. Suppose if you have input layer and hidden layers, I have the neurons like this. This is the another neuron. All the neurons are connected with the previous neurons. All the single neuron in the second layer, the hidden layer, is connected with the whatever the neurons available in the previous neural networks, that is layers will be connected. So in this way we can say that in a traditional fully connected neural network, every neuron in one layer is connected to every neuron in the previous layer. This creates a dense web of connections where every output depends on all inputs. Here, output of this will depends on all the inputs of the previous layer. In convolution neural network, however, this is no longer the case. Instead of connecting every input to every output, we connect each output only to a small localized region of the input. This we have seen it in the previous lecture. These limited and localized connections are referred to as sparse interactions, or we can call it as sparse connectivity. Only a small subset of weights participates in the computation of an output neuron, which leads to much fewer total parameters compared to fully connected architectures. Next, how sparse connectivity is achieved. Sparse connectivity is achieved by using a filter. We know that is called as a kernel of a fixed size that slides over the input. This also we have seen it in the previous problem. The filter defines a small window. Suppose if I have a 5 cross 5 image, if I am using the filter 3 cross 3 or 2 cross 2, I am going to slide over this, one by one will be moving out, and then we'll be finding out the best out of best features. The filter defines a small window that looks at just a portion of the input at any given time. At each spatial position, we compute a dot product between the filter and the local region of the input covered by it. Importantly, the rest of the input is ignored at that step. For example, if I have taken 5 cross 5 image and 2 cross 2, the kernel only that the cover image is only 2 cross 2, that we are going to do the dot product. As the filter slides across the input volume, it repeatedly connects only to local neighborhoods rather than the entire input. This limited receptive field ensures that each neuron in the feature map only interacts with a small region of the input, resulting in sparse connectivity across the network. Next, benefits of sparse connectivity. By reducing the number of connections between neurons, sparse connectivity provides a multiple advantages. The network needs to learn far fewer parameters, which significantly lowers the memory usage and speeds up the computation during training and interference. Few parameters also, if you are taking few parameters also, mean that the model has less capacity to memorize noise and irrelevant patterns in the data, resulting in better generalization and statistical efficiency. In short, the sparse connectivity enables CNNs to be much more efficient and less prone to overfitting compared to density connected, that is a densely connected models with the same number of layers. Next, local feature detection, how it has been done. Another key benefit of sparse connectivity is that it encourages the network to focus on local features in the input data. In image, for example, useful information such as corners, textures. If you are taking the entire image, so we are going to concentrate on the edges, corners, and the textures. We are going to concentrate it and we are going to extract it. So, so in images, for example, useful information such as edges, corners, and textures are usually found in short local picture arrangements. By limiting the receptive field to small window, the convolution layer examines precisely those local neighbors and learns to detect important local patterns. As we move to deeper layers, the network can combine the local features to form higher level model, more abstract representations such as shapes or object parts. This hierarchy of features emerges naturally due to sparse connectivity. Next, if you are taking one example illustration, to illustrate this concept, consider a 5 cross 5 input and a 2 cross 2 filter using the stride 1 and padding is 0. The filter is applied to the top left of the, so if suppose if I have the image like this 5 cross 5 image and the 2 cross 2 window if I have taken, first we are going to take the top left of the image, apply to the top left of 2 cross 2 region of the input and produces the first value of the output feature map. This then it slides of the step to the right and perform the same operation on the next to 2 cross 2 region. At each step, only the 2 cross 2 window of the input value is used, ignoring the rest of 5 cross 5 image. Because the filter will slide across the input 4 positions horizontally and 4 positions vertically, the output becomes 4 cross 4, 4 cross 4 image. This example clearly shows how each input is influenced by only 4 values, that is 2 cross 2, rather than all 25 values in the input. This hope everyone understood. Hyperparameters that control connectivity. The extent of sparse connectivity in a convolution layer is controlled by three important hyperparameters. The first one is the kernel. The kernel size determines the receptive field or how large the local region is. The stride, yes, the stride defines how far the filter moves after each step. A large stride keeps over more input positions and further reduces the number of connections. Next, padding adds extra zero valued pixels around the board of the input so that the filter can be centered on edge regions. Together, these hyperparameters allow us to fine tune how densely or sparsely the network connects to the input data and how large the output feature maps will be. Next, comparison with the fully connected layers. In fully connected layers, every input neuron is connected in the fully connected neuron is to the output neuron, making the number of parameters grow rapidly as the input size increases. This results in dense interactions where no spatial structure is leveraged. In contrast, convolution neural networks layer, the convolution layers only connect nearby input values through small receptive fields and shared kernels. These sparse interactions not only lower the parameter count but also preserve spatial structure, making convolutional layers much more efficient and better suited for tasks such as image and signal processing, where local relationship in data matter greatly. What you are taking out from this example, the final takeaway is sparse connectivity is one of the fundamental advantage of convolution neural networks compared to ordinary dense networks. By restricting the connections to local neighbors of the input, the CNNs require few parameters, reduced memory, and computational costs, and are able to extract meaningful local features that become building blocks for more complex representations. This local to global feature extraction mechanism, made possible by sparse interactions, is a key reason why convolution neural networks perform so well in computer vision and other real world tasks or the problems. Hope everyone understood. So the simply to say that how the 5 cross 5 image is reduced into the and how we are going to extract the very good features by applying the kernels on the original image. This is what the sparse connectivity explains. Hope everyone understood about this sparse connectivity connections in convolution neural networks. The remaining things we'll discuss in the next lecture. Thank you.